all, it's Didya Banuni, and I hope you had a very colorful Holi celebration yesterday. So, for the Holi celebration yesterday, I went to my cousin's house, and my cousin's house is about 25 kilometers away. You might be wondering, why am I telling you how far away my cousin's house is to my house? Well, it's because we can measure the distances in the cities in India, or like India to US, and so on and so on, because we have units like meters, miles, kilometers, etc. Whatever. But have you ever wondered, how do we measure distances between stars? Like, how do we measure how far away other stars are from our own Earth? Like, one star is 100 light years away, one star is a quadrillion light years away, and so on. How do we measure that? Well, that is the topic of this video. Okay, so I will delve into this topic. So, first I need to make you understand what is light. You probably already know light, right? Well, if you don't, then I'll just quickly explain. Light is the fastest thing in the known universe. Light is so fast that we measure enormous times that by a billion distances with how fast light takes to reach there. For example, light goes like around 6 trillion miles. In 1 year, light travels about 6 trillion miles. How big of a distance is that? That's how fast light travels. Give you a better understanding on how unbelievably, mind-blowingly fast light is, I'll give you another example. It took the Apollo astronauts 4 days to reach the moon. But if they were traveling at the speed of light, which is impossible by the way, they would reach the moon in just 1 second, because it takes light 1 second to go to the moon from Earth. Yeah, that's how fast light is. But how do we measure great distances? I always asked that question. So now that you know light, I will just again delve deep into it. So the first way that astronomers measure distances between our own world and other stars / galaxies is called trigonometric parallax. It's very complicated. Yes, it took me so much time to understand that. Just pronounce it, trigonometric parallax. So let's do a little experiment. Stick out your thumb like this, then close your left eye, and then open your left eye and close your right eye. You continue to do it. You will see that it looks like your thumb has moved, but more distant background objects just stay where they are. Yeah, your both eyes concentrate here. The mind just fills in between, just pluses them to get the in between of them. Close this and only this one, so that vision, so it makes a triangle, but when you close, one part of the triangle is missing. So just the vision of one of the other eye. The eyes combined equal the whole picture. Okay, anyways, distant stars are far away, more far away than the length of your arm, right? Yeah, they're way more far away. So you might think that astronomers put 2 telescopes on both sides of the Earth's equator and look at it, but Earth is a relatively small planet, and so we won't get that much of a difference. Yeah, you can't even see it. So we measure the distance of stars over 6 months, and also the universe is very big, so it can only do just a tiny fraction of it. I forgot to mention this too. The nearest star to our own sun which is Proxima Centauri, 4.24 light years away. Our own Milky Way, 100,000 light years. The nearest galaxy, Andromeda, 2.4 million light years away. space is very big, so it can only cover a tiny fraction. So like you measure it in summer and winter, and then you will get a change. It's like looking through your other eye. So that is how they measure close stars, okay? Close. Okay? But it only works for a few thousand light years. Beyond our own Milky Way, the parallax is too small to detect because of the great distances. So astronomers need another way of measuring the distance between stars, and that is called standard candles. Okay, another example, like and also standard candles are objects that we know the luminosity very well. Example, do you know the brightness of your light bulb, or luminosity? I'll call it luminosity. You know the luminosity of your light bulb, which is brightness, and let's just say it's like 10, nothing specific, just for example. You tell your friend to hold it and then ask him to walk backwards, to walk back like this. To you, it will look like the light bulb's light is decreasing, but it just stays the same. The actual light stays same. So the decrease in light your eyes receive is equal to the distance squared. Okay? So then by comparing the light you receive and the intrinsic luminosity of the actual light bulb, which is 10, you can calculate how far your friend is. Okay? The light bulb is 10, now you measure 3, you can calculate. Now you see 3, now you can calculate. Okay? That is standard candles. So, in the universe, our light bulb is a special type of star called Cepheid variable. Cepheid variables, stars, are internally unstable. So, they're kind of like a constantly inflating and deflating balloon. Sometimes they inflate, sometimes they deflate. So, we can calculate the brightness by measuring time between two periods, from inflation to deflation. So then we can calculate the brightness, and then we see what we observe and the actual luminosity, and then just calculate. That's simple, right? But this only works for like 40 million light years. Beyond that, the stars just are too blurry to resolve. So we need another type of standard candle, and that is called type 1A supernova. So you probably know supernovas, but if you don't, I'll just quickly explain. Supernovas are one of the ways stars die, if they're not big enough to be a black hole, but something. Okay? It's just, you probably know, okay? So it's just one of the ways stars die. That's simple. A big kaboom, big bomb, big explosion. Yeah, that's what I was trying to say. So the type 1A supernovas can be used as standard candles because more luminous ones fade slower than less luminous ones. And I forgot to mention this in the Cepheid variables. More luminous ones contract slower than less luminous ones. Okay, so then we can use that to advantage. Just measure, do the standard candle stuff, and then boom, get it? Supernova. You can see the distances, calculate them specifically, and that's the end of the video. But wait. JK, that's not the end of the video. Why do we need to measure those distances? Well, do you remember how fast light is? It takes like 8 minutes to reach from the sun to us. So, if you look at the sun, you're seeing what the sun looked like 8 minutes ago. It will take another 8 minutes to see what it looked like when you were standing. But by then, it will be 8 minutes after. Okay? So, if you look at the Big Dipper, you're seeing what it looked like 80 years ago. Go by that logic. Those smudgy galaxies, millions of years. So, in that sense, the universe is an inbuilt time machine. The further we look back, the younger the universe we're probing. The universe is constantly sending us information through light. All that remains is for us to decode it. And that is the real end of the video. I hope you like it. If you do, smash that like button and hit the subscribe button so you never miss any new videos. For now, I'll see you later. Bye.